Good morning, everyone. My name is Pamela Cambianica. I'm a postdoc at the Astronomical Observatory here in Padova. And today I'm going to present a very recent project, it's just 2 months old, named ANTHELIA, which aims to understand, to study the complex illumination and thermal environment of lunar pits and lava tube. But just a quick thing, I would like to, I'm sorry, I forgot to mention 2 persons here, Cristina Re and Adriano Tullo from the National Institute of Astrophysics as well. Super sorry. Okay, I would like to start this presentation with a bit of background. As you are aware, the human return to Moon is fundamental to understand all the geological processes, including volcanism, that modify the crust of our satellite. But the very important question here is if the Moon can be safe for astronauts. And the answer is that it's a very difficult task because basically for 3 reasons. The first one is radiations. Just an example, astronauts in spacesuit would be exposed to 60 microsieverts of radiation every hour, and is up to 150 times higher than on Earth. And the second reason is micrometeorite bombardment, and of course, the extreme lunar thermal environment. In fact, the equatorial regions experience diurnal temperatures of about 300 kelvins. For these reasons, lunar lava tubes are considered as excellent natural candidates for future human exploration to shelter astronauts for both meteorite impacts, radiation, and temperature. So we have to study the subsurface of the Moon to investigate, to identify which are the best conditions in terms of depth, size, latitude of lunar pits and lava tubes to understand, to offer a stable and safe place to stay. Okay, in this very quick video, you can see the lava tube formation during the Geldingandalur eruption in Iceland. As you can see here, the lava flows tend to become channeled into a few main streams. Then the overflows of lava cool and solidify, creating stacked layers of lava around the flow. And the lava melts downward into the ground, giving the tube a taller and narrow cross-section. Then a solid crust can form overhead and enclose the tube, and the tube then insulates the flowing lava within. And after the eruption subside and the flows harden. Okay, and then as a result of structural instability triggered by tectonism, impacts, and seismic activity, the roof of such void spaces can collapse, forming pits. Okay, another very important question: if a lunar collapse pit may provide access to subsurface lunar tubes networks. Up to now, there are 16 confirmed collapse pit features on the Moon. They are located in the equatorial regions, sizes ranging from 15 to 150 meters. And most of them have verified overhangs. This means that suggests that they could be opening to lava tube networks. This is the starting point for ANTHELIA. In this project, we aim to characterize the complex illumination and thermal environment, as I said before, for different reasons. First of all, to support future lunar missions and to improve our understanding of lunar caves' thermal behavior, to investigate the link between size, morphology, latitude with the thermal behavior, to study the thermal stress they undergo as a result of temperature changes, and then investigate the extent of any temperature changes to identify what the depth of the tunnel might be to ensure a thermally stable environment. ANTHELIA is divided in 3 main steps. The first one is the definition, of course, of the geometry. We started with two-dimensional geometry of a pit, and flat floor pits are treated as a cylinder with a different entrance size, slope of the walls, and depth. And then we will add boulders and collapsed material to the floor to understand which is the link between their presence and the variation in terms of thermal temperatures. Then we will move to 3D models by applying the 3D PD photogrammetric pipeline developed here in Padova using the Lunar Reconnaissance Orbiter camera image pairs. And here you can see an example of one digital terrain model of an inverted river around Aeolis Planum on Mars. And okay, then we defined the materials. Of course, we selected the lunar regoliths and basaltic rock. And due to the fact that there might be ice cold trap in Moon, not just at poles, as you know, but also inside permanently shadowed regions in high latitude caves, we decided to include water ice patches in the matrix at different depths. Okay, the second step is the definition of the illumination model, a ray tracing illumination model. We included both the direct illumination case depicted here in orange and also the backscatter and ray radiation. The reasons for that is that it's fundamental to include the backscatter radiation because of the self-heating effect. As you know, the self-heating results from the absorption of thermal radiation by all the elements of the topography from the surrounding visible portions. This means that the temperature increases due to the fact that the coldest spaces can be heated by the hot ones. I can show you an example of the results we can obtain by applying our model. We decided to apply the model to the Fuller crater located on the Mercury's North Pole. And as you can see here in this column, on the left column, you have the total amount of solar insolation received by a crater. And on the right side, you have the backscatter radiation. And as you can see, there are shaded areas that receive the 100% of the reflected radiation. And this results in an increase in temperature. And this is a very important effect we need to take into account, especially for very complex ambient like caves and pits. Okay, then the radiative maps are fed as boundary condition to COMSOL multiphysics, a finite element model to understand, to calculate which are subsurface and surface temperatures throughout the lunar day. And okay, as I said, it's a very young project, so I can show you actually results, but I can show you where we are so far. So we run time-dependent 2-dimensional and 3-dimensional thermal models, 2-dimensional models to simulate steady-state equilibrium of a pit, and the 3D models to provide dynamical thermal variation of the pit. We decided to simulate the Tranquillitatis pit in Mare Tranquillitatis. The reason is that we can compare our result with those obtained by the Diviner instrument aboard the Lunar Reconnaissance Orbiter, and to compare with the findings from Horvath et al. In 2022. And as you can see here, Tranquillitatis pit is a very comfortable place to stay because there are no very high temperature variations, but temperature remains stable at 17 degrees Celsius. But as I said, it's a work in progress. And in the future, we will play with different geometries, with latitude. We will include also caves in our models, and we will study the volatile stability. The third step of this project is the application of the volatile transport model developed by Prem et al. In 2018 to investigate the volatile stability in different thermal behavior, and with a Monte Carlo simulation, try to study the migration and trapping of the water vapor. Okay, to conclude, the human return to the moon is pivotal to improve our knowledge about the moon evolution. Lunar pits and lava tubes are the very natural shields that can safely accommodate future astronauts. And in this context, the ANTHELIA project aims to study their thermal environment to find the most favorable condition for this purpose. And I would like for your attention.